What if the single invention that sparked today's AI explosion was never meant to think at all? Picture a tiny silicon chip in the late 1990s, designed to draw a few extra polygons for gamers, suddenly becoming the brain behind music composition, disease diagnosis, and self-driving cars. Few imagined that a processor built to paint tiny textures could become the future's nervous system. The story kicks off with an unlikely partnership between a visionary named Jensen Huang and a humble piece of silicon that would soon rewrite the rules. As the first prototypes hummed to life, no one could foresee the chain reaction that would ripple across every industry. How did a modest ambition collide with an exploding demand for realism, and why does that matter for us today? The next chapter shows how that collision set the stage for a technology that leapt far beyond its original purpose. In the early 1990s, personal computers were just beginning to show color graphics, yet they were stuck with flat, simple images. Game developers begged for richer worlds, and manufacturers scrambled to keep up. Jensen Huang, a former LSI logic engineer, co-founded Nvidia in 1993 with a single goal: build a chip that could lift the heavy lifting of image calculations off the CPU. The result was the NV1, a device that bundled two-dimensional, three-dimensional, and audio processing into one package, a novelty at the time. Yet the NV1 struggled, selling barely enough to keep the company afloat. The turning point arrived in 1999 with the GeForce 256, marketed as the world's first GPU. This chip introduced programmable shaders, letting developers write code that directly controlled how light and shadow behaved on screen. Imagine giving an artist a paintbrush that could also calculate the physics of every brushstroke in real time. That was the power of the new GPU. That breakthrough turned graphics from a static visual layer into a dynamic, interactive canvas, and set off a cascade of innovations that would later redefine computing itself. This momentum carries us into the next era, where parallel processing reshaped everything. The real secret behind the GPU's later impact lay in its architecture: thousands of tiny cores working side by side, each handling a fragment of a larger picture. While CPUs excel at sequential tasks, think of a single highway lane moving cars one after another, GPUs resemble a sprawling network of side streets, each allowing a vehicle to move independently. This parallelism, originally designed for shading pixels, became a perfect match for the math behind machine learning, where massive matrices must be multiplied millions of times. In 2006, researchers at the University of Toronto realized that the same parallel engine could accelerate deep neural networks dramatically. They swapped a modest CPU for an off-the-shelf Nvidia graphics card and saw training times shrink from weeks to hours. Suddenly, the dream of teaching computers to recognize objects, translate languages, and predict patterns leapt forward. The GPU, once a tool for rendering exploding graphics, had become a universal accelerator, turning once impractical algorithms into everyday services. Next, we'll see how everyday gamers inadvertently became pioneers of this new frontier. While academia was tinkering with GPUs for AI, gamers were already pushing the hardware to its limits. The launch of Crysis in 2007 promised to be the ultimate benchmark, boasting graphics so demanding that even the most powerful rigs faltered. Players built GPU farms in basements, overclocking cards, tweaking voltages, and swapping cooling systems to squeeze out a few extra frames. These enthusiasts unintentionally became test pilots for extreme parallel processing, documenting thermal limits, power draw, and failure points in real time. Their findings filtered back to Nvidia's engineers, who used the data to fine-tune driver algorithms and improve chip reliability. In a sense, the gaming community acted as a global, crowdsourced R&D department. The race to render realistic water, fire, and shadows forced Nvidia to innovate cooling solutions, power management, and real-time ray tracing, all technologies that today power scientific simulations and autonomous vehicle perception. The line between entertainment and engineering blurred, and the world's most demanding gamers became accidental contributors to breakthroughs that would reshape medicine and finance. This momentum carried forward into an even stranger arena: cryptocurrency mining. Just as gamers were driving demand, another unexpected group discovered the GPU's hidden talent: cryptocurrency miners. In 2013, early Bitcoin adopters realized that the hash calculations needed for mining could be parallelized, and they began swapping CPUs for graphics cards, which could perform billions of hash operations per second. The GPU's ability to handle massive, repetitive math made it a far more efficient miner than traditional CPUs. By 2017, the boom of Ethereum and other GPU-friendly coins turned entire warehouses into humming halls of mining rigs, each packed with dozens of Nvidia cards consuming megawatts of electricity. This surge forced Nvidia to grapple with supply shortages, prompting the company to release a line of CMP cards specifically for crypto mining, separating them from consumer graphics. While the crypto craze created market volatility, it also accelerated the development of more energy-efficient architectures, as miners demanded lower power draw per hash. The unintended consequence: a new generation of GPUs that could deliver higher performance while sipping less electricity, a boon for data centers running AI workloads today. In a twist of fate, the speculative world of digital currencies became a catalyst for greener, faster processors that now power everything from weather forecasting to personalized medicine. The ripple effects continue into everyday life, as we'll explore next. Few realize that the same GPUs fueling AI chatbots also enable doctors to analyze MRI scans in seconds rather than hours. By training convolutional neural networks on thousands of medical images, radiologists can now spot early signs of disease with a confidence level rivaling seasoned specialists. Another surprising fact: Nvidia's GPUs sit at the heart of modern film post-production, allowing visual effects studios to render complex simulations, like realistic smoke or water, so quickly that a blockbuster can be finished weeks ahead of schedule. Finally, the company's push for high-speed interconnects, originally meant to link multiple GPUs for smoother gaming, now underpins the massive data pipelines of climate models, letting scientists simulate ocean currents and atmospheric changes with unprecedented resolution. Each of these outcomes traces back to a chip built to make video games look prettier, highlighting how a single engineering decision rippled outward, reshaping fields nothing like its creators imagined. Next, we'll bring the story down to the everyday experiences of ordinary people. What does a GPU-powered AI model mean for the average American? When you ask your smartphone for a photo edit, a neural network processes the image in real time, sharpening details and removing blemishes, all thanks to the parallel cores honed for game graphics. In grocery stores, self-checkout systems use computer vision to identify items, a technology that owes its speed to the same algorithms accelerated by Nvidia chips. Even the navigation app that suggests the fastest route during rush hour relies on AI predictions trained on terabytes of traffic data, processed by GPU farms spread across the country. Moreover, the surge in remote work has led businesses to adopt cloud-based AI tools for everything from automated customer support to fraud detection, all running on the same hardware that once powered high-resolution gaming. In short, the silent workhorse hidden inside data centers is influencing the convenience, safety, and efficiency of daily life for millions of people across the United States. I've personally seen this when my own photo editing app transformed a blurry vacation snap into a crisp memory within seconds, something that would have taken ages just a few years ago. Up next, we'll bust some common myths that still linger around this technology. One common misconception is that GPUs are only useful for graphics. In reality, their parallel architecture makes them indispensable for any task that can be broken into many smaller calculations. Think of them as a massive team of accountants each handling a line item, rather than a single clerk processing a ledger sequentially. Another myth assumes that AI breakthroughs came solely from software, ignoring the hardware that made those algorithms practical. Without the raw processing power of GPUs, deep learning models would remain theoretical, locked behind prohibitive training times. Recognizing that hardware and software evolve hand in hand helps us appreciate why a graphics card originally meant for gamer enthusiasts now powers autonomous cars and genome sequencing. So, are we still underestimating the true reach of these chips? Next, we'll glance at where this evolution is headed. Looking forward, the next generation of Nvidia chips promises to blur the line between CPU and GPU even further, integrating dedicated AI accelerators that can process trillions of operations per second while consuming a fraction of the power. Imagine a laptop that can run complex language models locally, without needing to stream data to the cloud, a reality that could protect privacy and reduce latency. Meanwhile, advances in silicon photonic interconnects aim to link GPU clusters at the speed of light, enabling climate scientists to run Earth system models in near real time. As quantum computing matures, GPUs may serve as the bridge, handling tasks that are still too noisy for quantum bits. Over the next decade, we can expect autonomous vehicles to become commonplace, powered by onboard GPU arrays that interpret sensor data instantly, and personalized medicine to deliver treatment plans computed in the clinic. The accidental birth of the GPU has set the stage for a future where computation is as ubiquitous as electricity. This brings us to our final reflections. From a modest graphics card meant to add a few extra shadows to a video game, Nvidia inadvertently built the engine that now drives AI, scientific discovery, and everyday convenience. The journey shows how a single technological gamble can reshape the world in ways its creators never imagined. If this story surprised you, smash the like button, tell us in the comments which GPU-powered gadget has impacted your life the most, and subscribe for more deep dives into the unexpected twists that have forged our modern world.